and it's spinning around, right? So it's spinning this way, and it's spinning around. Bigger. Spinning around in a circle like that. Right? Spinning, spinning, spinning. Spinning around. Okay? How quickly is it spinning? Well, in order to answer that question, we need to know the value of B naught. So let's say B naught is a 1.5 Tesla magnetic field. How quickly is this spinning? Right, we're going to need to use that equation. So our precessional frequency is going to be equal to the gyromagnetic ratio times our magnetic field, in this case B naught. So what is the gyromagnetic ratio?
42.57 megahertz per Tesla.
All right, I didn't hear enough people, Jared. Let's try that again. What is our gyromagnetic ratio?
42.57 megahertz per Tesla.
All right. A little bit out of phase, but that's okay, we'll work on it. So, we have our gyromagnetic ratio here, and we have our B naught over here. So what is our precessional frequency?
$63.86 megahertz.
Okay, I heard 63.86. Does everyone agree?
Yeah.
Are you sure?
Yeah.
Yeah.
63.855.
63.86. And what is the unit?
Megahertz.
Megahertz. That's it?
Yes.
Yes.
No per Tesla?
No.
Tesla's already there.
Very good. No per Tesla, it's just megahertz.
So the V is the W, not on the equation.
V is what, yeah, it's what you're
It's a
going
W.
for. It's that,
Oh, was it a W? Ah,
It was a W.
It's supposed to be a W. That's my fault. Wrong. So, let me just fix that.
so typically you're given the Tesla string, and then you just have to remember that 42.57.
Correct.
Because it's for hydrogen. They won't ask you like on the registry for another atom.
They should not. But if they do, they will give you the gyromagnetic ratio.
Okay.
And so you just do it exactly the same way.
Same thing.
Okay. So now we know how quickly this hydrogen is spinning, right? It's spinning like this, 63.86 million times a second. Now over here, I've got some RF energy. Right, so here's some RF energy. Whee. And this RF energy is going at 42.57 megahertz. Am I going to have resonance? Will these two resonate? Why not? They're not the same. All right. What if I bump this up to 60 megahertz? Are they going to resonate? Getting closer. All right, getting closer. What if I bump this up to 63 megahertz? Will they resonate?
Maybe.
We're getting closer, but it's not there yet. Not there yet. Well, what if I bump this up to 63.5 megahertz? No?
No.
6 megahertz? 7 megahertz?
No.
0.8 megahertz?
No.
0.85 megahertz?
No.
0.86?
Yeah.
It has to be the exact number.
Right, so
So,
yes, it'll have to match exactly. Right, so the frequencies have to match exactly. Yes.
Mr.
Sarah.
Clark, when do we use that resonance when we're scanning? What is going on when we're looking at the scans and they're changing this?
Alright, so then what's happening is, as soon as we match it, this arrow here begins to move like that. Right? So we move the arrow in this direction.
Counterclockwise?
So we're moving it away from, well, it could be this way too, doesn't matter.
Okay.
But the idea is that we are moving this arrow away from the longitudinal plane. Remember, this is longitudinal. And we're moving it into the transverse.
So the longitudinal is made by the main board, the main magnet. RF is what brings it into the.
Into the. No, RF is just what moves it away from the longitudinal. So yes, it is going to go towards the transverse. Right? Transverse is kind of like the floor. Longitudinal is kind of like pointing straight up at the ceiling. So over time, we're going to go from this to that. Right? RF energy is going to move us from here to here. If we keep the RF energy on, we could even go like that. Right? So we can go from 0 degrees to 45 degrees to 90 degrees, which is transverse, to 135 degrees, all the way to 180 degrees. Right? We can go fully away from the longitudinal, or we can go fully anti-parallel to the longitudinal plane. Right? We're back longitudinal, but pointing in the opposite direction. Right? So we can go all the way like that. And in fact, if you leave it on, you can even go further. Right? But that's a story for another time.
Is it until it resonates with the number, or until there's a balance?
So, no, the only time it will stop is when we turn off the radio frequency here. Right, so this blue, right? This blue is our radio frequency pulse. This is our RF pulse.
And we're setting that at the console.
And you do this at the console.
And this is called a flip angle, right?
Correct. So the green here is our flip angle.
Is the flip
Yes, the flip angle is created by the RF pulse resonating with the precessional frequency of our hydrogen.
So the RF pulse has to be exactly the same as
To get the flip?
the megahertz?
Correct.
And when does the K and happen?
All right.
When you let off the RF frequency.
Exactly. So as soon as we turn off the RF pulse, right, we're gonna stop flipping it, right? It's gonna stop moving downwards. And at that moment, as soon as the RF is gone, we are gonna get our free induction decay. We're gonna begin our T1 recovery. We're gonna begin our T2 decay. So T1 recovery is gonna start moving back, and T2 decay is gonna start going out of phase. It's gonna start spreading out. Right? So if you've got a whole bunch of hydrogens here, right, all pointing in this direction, as soon as you let off the RF pulse, right, they're gonna start slightly changing which direction they're pointing. Right, and it's all because of those spin-spin interactions. Hydrogens bump into each other, they knock each other slightly out of position. Yes, Patricia.
So the direction of the hydrogen atom, one precessional and one QAGO,
Mhm.
that's two different directions within one hydrogen.
Right. So the hydrogen atom, right, it's spinning like this, right? So as soon as we apply our RF energy, it's going to start going like this. It's not spinning like this, right? If you keep applying RF energy, this is going to keep going lower and lower and lower, right? You stop the RF energy, now it begins to decay. So this is going to start going back up. It's going to start going back up. What is this called? Not T2.
T1.
T1.
No.
This is T1 recovery.
Read that.
This is T1 recovery. Right? Now, imagine you had a whole bunch of me's spinning around doing that exact same thing, right? we would not all be pointing the same direction. That would be T2 decay. Okay? Now, because it's very easy to get dizzy doing that, right? And because it's hard to show that kind of motion, normally we don't like to draw our nuclei spinning around like that. What we do is we use a frame of reference where it treats the nuclei like it's still, right? So just imagine you've got a camera here, right? Filming my arm. If Papita was holding the camera filming my arm, right? She would see this arm spinning around, correct? But what if the camera was right here? Would the camera see the arm spinning?
No.
No, the arm's gonna look still, right? It's gonna look like in the same place. So that's what we are doing when I'm saying, all right, you're doing this and this, right? When I'm saying that you've got T1 recovery like this, it's spinning, but I'm treating it like the camera's following as it spins. So all you see is it moving up and down. Does that make sense? So yes, in reality, it's gonna spin, it's gonna spiral, but as far as my demonstrations go, I'm treating it like we're following it as it spins. So you'll see me say, okay, RF pulse, transverse plane, recovery, recovery, right? And you won't see me spin because I'm just treating it like we're still. But yes, RF pulse knocks them into the transverse. T1 recovery lets them recover. T2 decay, they spread out, they don't point in the same direction anymore. Any other questions? Are we kind of okay with this concept now? If I gave you a pop quiz, would you do okay?
I'll let it marinate.
Alright, well, I guess that's why we're not doing a pop quiz. Okay. So, if we don't have any more questions here, I would like to actually get a head start on the next unit. Is that okay? All right. Do we need a break? It's 8 o'clock right now.
Yes.
All right.